In this video, we're going to talk about timers. Timers are very useful in that they allow the processor to um, determine, without having to sit in a loop and count the number of instructions and figure out how long things are taking. A timer, we can turn on a timer and we are able to read the timer to figure out how long has it gone by since the start of the timer. Also, we can enable these timers to interrupt the processor at any point of time. We can set a set time and have the processor perform a task on a regular basis using timers while the processor is doing other things. So I think the best analogy would be if you are using the oven, baking a cake, let's say. You don't want to have to sit there and watch it every minute at a time. You want to be able to set the timer to 30 minutes, go off and come back and take care of it. Or another example would be when you're going running, you do not want to have to be looking at your watch all the time. You want the timers to kind of take care of how long you've been running, and let you know when you have reached your goal. Those are kind of human examples of how we use timers. Computer use it exactly the same way. For example, if operating system wants to let a process run for a certain amount of time before passing control to another process, timer would be very useful. In our case, with this microcontroller, that microcontroller may be controlling multiple things or may have to do multiple things, where each item takes a very small amount of time to do, but has to be done on a regular basis. A timer is a wonderful tool to do that because you set it to the next time you have to perform the task, and the timer could interrupt you, the processor, and the processor can take off and get the job done. So how many timers do we have in this particular case? Most processors have many timers, the same as the PICmicro that we are using here. In our case, we have 4 configurable timers. Some of them are 8-bit, some of them are 16-bit, some of them could be either, depending on how we configure them. And almost all of them will have a register that controls the configuration. They're gonna have 1 or 2 register which actually keeps the count like a timer. When you start it at 0, goes 0, 1, 2, 3, 4. Some that we have 1 or 2 register depending on whether they're 8-bit or 16-bit counter, which keeps track of how far along you are. And then of course, each one of these timers have a set of interrupts associated with, much like the peripheral interrupts int 0, int 1, and int 2 that we talked about in the earlier video. Here you could also have these timers we have 4 timers: timer 0, timer 1, timer 2, timer 3, and each one of them could have a interrupt. And the way it works, once you enable all the interrupt and you put a value in the timer count increments by whatever you configure the timer to, however long you want the timer to take to increment. And then when it increments all the way from where it is to the largest number, in case of an 8-bit, the largest number would be FF. So and in the case of a 16-bit, the largest number is going to be FFFF. So for an 8-bit system or a timer, the counter, you can start the counter anywhere you want. This would be the timer register or the timer count, and this count increments. Once this count for an 8-bit system, once this count reaches 1, 1, 1, 1, 1, 1, 1, the next count will put it at 0, 0, 0, 0, 0, 0, 0, 0. At this time, it will cause a timer interrupt. That, of course, depending on whether you set it to high priority or low priority, is going to jump to the low priority or high priority vector in the program memory location 8 or 18. Now, what happens if you have a 16-bit, or you've configured your timer as a 16-bit, all you do, you set whatever count you want in here, that count ups until it reaches, and I'm going to do this in hex, 0xFFFF, since it's 16-bit. And on the next tick of the clock, which is not the same as the oscillator, when we're going to talk about that, the next clock is going to go to 0x0000, and at the same time is going to cause timer interrupt. Okay, so pretty straightforward. You always can read the timer count as it's timing up if you like, but commonly the way we use them, we set this number in here such that we get enough time that we are looking for, and then at the transition from FF, in the case of 8-bit, to 00, a timer interrupt happens, and in the case of a 16-bit, when it goes all the way to FF, it causes an interrupt. Okay, so that's pretty much the overview of it. Each timer is a little bit different from the other timer. We're not going to go through all the timers in detail, because once you learn one timer, the other one are just pretty much the same as that one with slight modification. But what I would like to do, take a few minutes and give you kind of the overall view of the different timer, and then come back and focus on timer 0 as an example of how actually you set it up, configure it, and have it cause you an interrupt. So let's go ahead and take a look at the timer. What type of things do you have in a timer? So every timer, this is timer 0, one of the 4 timers. You're going to have a control register, typically referred to as T0 control, and then you're going to have 2 registers, or 1 register. If you're 16-bit, then you're going to use the low and the high. If you have an 8-bit, then you're just going to use the low. And that's where the count is kept. Every time the increment happens in the timer, that's where the register you can go read to find out where the count is for this particular timer. So let's take a, so this is the T0 control register, and look at it. It says, okay, timer 0 on or off. That's the first bit, just tells you whether you turn it on or off. T0 8-bit says, do you want me to run this thing as an 8-bit, just looking at timer low, or do you want me to put the timer 0 high register next to timer 0 low and treat it as a 16-bit? So this is the register that, this is the bit that allows you to do that. Now, you can run this thing off of an external clock. So, or you run it as with an instruction cycle. So most of the time we run it as an instruction cycle down here. So 0 is what goes in there. And then we can also select, if we were using external pinned clock coming in, actually in this way you can use it as a counter, but because as the pulses come in, you can count them. And also you can, if you're using the external, which we typically use the internal for what we are doing in this video and this course. But if you were using the external, you can choose whether the rising edge or the falling edge, depending on whether you put a 0 or a 1 in there, is really causing the increments in the timer 0 values. Now, one other nice thing this has an ability to let you, instead of having to react to every clock, by setting these pre-scaler value to 1, you can say use the pre-scaler, which basically says, let's say if my clock is 1 microsecond, my oscillator clock is 1 microsecond, my instruction cycle is 4, therefore 4 times the time, if the T oscillator, let's say, is 1 microsecond, and therefore the T time of instruction cycle is 4 times TOS, right? Which is basically 4 microsecond. I can have the clock increment its value, or the clock tick, each clock tick be 4 microsecond. In that case, I just basically said don't use the pre-scaler, it just uses that. Or I can say let's use a use a 1 to 2 pre-scaler, which then each tick of the clock will take 2 times 4 microseconds. So each tick of the clock will be 8 seconds. So that's kind of a useful thing to keep in mind. And here is a little circuitry for the 8-bit. The 16-bit is very similar. Basically, we are using, with the way we set it, we are using the internal clock oscillator, and this basically says the period of this clock is 4 times T oscillator. The frequency is a fourth, which means the period is 4 times larger. And then if we select the prescaler, this is where the prescaler is embedded. There's some synchronization, and that drives the timer 0 register. In this case, it's an 8-bit register. It increments it every time. Okay. Now, if you wanted to use interrupt, and you basically go make sure that all the global interrupt, peripheral interrupt, priority interrupt, all that is enabled, and then remember we used to use int 0, for example. Now we can go say, okay, enable the timer interrupt, and clear the timer flag, and that's pretty much it. Somewhere in, and then somewhere else we would have a flag that we can go ahead and say that would be an int con 0. You go ahead and set the flag to be either a high priority or low priority, and there you go. You got an interrupt running for yourself. Okay, and so that's that, and that's a kind of an overview of this one. Let's talk a little bit. So let's say we decide, just an example, we decide, well, we're gonna enable it as an 8-bit. We're gonna turn it on. Turn it on. So bit 7 would be a 1. We're gonna enable it as an 8-bit, and we're gonna what else we're gonna do? So now we got an 8-bit machine timer, and then we're gonna say select. Yeah, we don't really care. We're gonna use the internal, so that's gonna be 0. We don't care, so we put whether it's because we're not using the outside pin coming in, so I'll raise your leading or trailing won't matter. PSA, yeah, let's go ahead and use a prescale just for an exercise, and let's say we use 0, 1, 1, which basically is 1 to 16 for us. Okay, and let's say we are using the default clock. So the default clock we have is 32. So T oscillator is 32 microsecond, and based on the prescaler we are running as an 8-bit timer 0. And then what else did we decide? And we decided that the prescaler is 1 to 16, so the prescaler is set to 16, 1 to 16s, and that's pretty much it. Now another question is, let's say I write in timer 0 low, let's say I write 25 decimal. Okay, so what's going to happen? This means that in my timer 0, actually let me make my life easier, and I'm going to write 56 in here. Okay, so that basically says I'm going to put in this timer 0 56, which means it's going to increment. When this 56 is going to keep incrementing, when it reaches 255 FFF, and then it goes to 256, which is going to be 0, this is where my interrupts will happen. So if I'm starting from 56, my interrupt will happen 200 ticks, 200 clock ticks later. Now the question is, how long is a tick? The duration of a tick is determined by 4 times the oscillator speed. If you're using 32 seconds, that would be 32 times the PSA, the prescaler that we are using. So in our case, it's going to be 4 times 32 times 16, which and these are all in microsecond. So that would be basically whatever number that is. So this works out, if I did my calculation correctly, that is 2,000 48 microsecond. So each tick, each increment of this will take 2048 microsecond. So before I get my interrupt from timer 0, it has to tick for 200 times. So the duration before interrupts, it's gonna be 200, the tick, 248 for each tick times 200 microsecond. So that's how long this thing is gonna wait before it causes me an interrupt. If I do the multiplication, it's gonna be 2048 microsecond per tick times to 200, this should be 200, actually let me erase this, 200 ticks. And that'll give me 0.4 seconds, and that's how long it's going to take before an interrupt happens. Let's go ahead and do one more example, do a little overview of the rest of the timers, and that would conclude this video. So let's say here's another example for us to work through. Let's say they gave us T0 con as 87. What's 87? 87 is basically 1, 0, 0, 0. 7 is 0, 1, 1, 1. So this is T0 con. So this, I remember, it's basically saying that this is saying the bit 7 is saying that turn on. The timer 0 is on. Let's go ahead and see the rest of the zeros. 0 says it's in a 16-bit mode now. Okay, so we are in a 16-bit mode. We are using internal, and we are using it really doesn't matter because we're using internal clocks. So basically this, we're saying that we are in 16-bit mode. Next one, it's saying we're using an internal RC, which all is telling us that TOS is, the oscillator is set to 32 microsecond. And then let's go ahead and take a look at that and see what else we got. PSA set to 0. Oh, prescaler is assigned. Last time I should have really called this one 0 as well. So because we wanted to use the prescaler. So the prescaler is used, and then the prescaler is set to all ones, 1 to 256. So this basically says use prescaler, and this says set it equal to 256. Okay, great. The question is, how long does it take for timer 0 to increment timer 0 by 1, so a single click. So that's the tick. If you remember, the equation for the tick will take how long it takes for a single tick. It's going to be 4 times T of oscillator times the PSA. So in our case, we've got 4 times 32 times 256 microsecond. So if you multiply all this out, it basically says, hey, each single clock increment will take 3, 2, 7, 6, 8. Now the second part of this is saying, hey, what do I have to do to get a delay of 640 milliseconds before this interrupt happens? We know this means we have to find out what we are putting in timer 0, and we got to make sure we know how many of these ticks do we need for 640 milliseconds to happen. So the first thing I got to do, I got to find out the number of ticks I need. And the way I do that, I say, okay, you want 640 milliseconds, but 640 is 640 to the power of 3 microsecond. And each one of my ticks are 3, 2, 7, 6, 8 microsecond, which basically tells me F E C. So if I set that in there, my expectation is after 20 ticks is going to get here, causes an interrupt, which tells me I've got 640 millisecond in here. Let's recap this. So the first thing we did, we calculated the number of ticks I need, which was simply the 4 times TOS times PSA that was set. And then I had to go back and figure out how many ticks do I need, and then subtract that from 1000 to find out where I need to be in order to get 20 ticks, which gives me 640 milliseconds. Okay, so that was an example. We spent a lot of time talking about timer 0. I just want to kind of briefly mention the other timers. Timer 0 is pretty flexible. You can set it to 8 bits, 16 bits. You can have PSA, not PSA. Timer 1, it's only 16-bit. That's the only mode you can use it. It's got more or less a little less flexibility, but it's pretty good for all kinds of functions. Timer 2 is 8-bit with similar functionality, and it's got other functions. So for example, when we get to talk about PWM, you're going to find out that we're going to use timer 0. Again, each one of these have their associated interrupts to enable. For example, in this case, you will have a timer 2 interrupts that you need to enable and configure and all, set the flags and all of that, which is in these registers below. All of this material comes from the data sheet, so you're more than welcome and encouraged to go there and explore it even further. And timer 3, the last interrupt we have, can be either 8-bit or 16-bit. And again, this timer is shared with a lot of functionality, other functionalities such as the comparing and all the other serialization of data and all of that uses this particular, even A to D converters use these timers to help in the process. And again, it's got its own set of registers to do the various things it can help do. And here's a listing of these registers. That brings us to the end of this particular video. What we did, we just started by talking about the timer and how, what the different features are that the timer, the different configuration that the timer can have. We spent a fair amount of time talking about timer. The bottom line being is that each timer has a count register. In this case would be timer 0 low, timer 0 high. Whatever you put in there, it's going to be incremented by however long a tick is, and every time the tick comes along, it increments it by 1. Once it overflows, goes from the maximum number back to 0, that's when the interrupt happens. So, and then we had an example down here of how to do that. Anytime you have questions, you look at these bits and figure out which bit to set to what value to get whatever tick duration, or however, whether you want it to be 16-bit or 8-bit. That brings us to the end of this video.